We're going to talk now about Eulers equation. Euler's equation is the momentum equation for a fluid with no viscosity, or an inviscid fluid. So we start with the Navier-Stokes equations and we neglect viscosity. So we remove the viscosity term from the Navier-Stokes equation. And that's how we get Euler's equation. It's a very simple derivation. We just cancel one term. But the implications are important because this type of system is much easier to solve than the Navier-Stokes equations. Now, we're going to start by looking at what we call streamline coordinates. Streamlines are very convenient graphical pictures of flows, and it represents a logical coordinate system. So we have the direction of flow, s, so the s coordinate is along the streamline, and the n coordinate is perpendicular or normal to the streamline. So because flow always goes along streamlines and never normal to a streamline, we know that the velocity in the n direction is 0. And the only velocity is in the s direction. So that's v, the velocity. So this is analogous to x and y coordinates, where you'd never have any velocity in the y direction. Velocity is only ever in the x direction. So we can actually simplify this a little bit. We have our radius of curvature, which is r, as you can see in the diagram. And we come up with equations for streamline coordinates for both coordinate directions, one in the s direction and one in the n direction. Now, we could note that this normal acceleration is v squared over the radius of curvature, and that just comes from classical physics. So if we neglect the effect of gravity, then we can see that the pressure change in the normal direction just comes from curvature. Now if there's not much curvature, which means the radius of curvature is very large, it becomes infinite for a straight streamline. If r is infinite, there's no pressure change normal to a straight streamline. So that tells us something important. What that tells us is that the pressure increase normal to a flow is what turns the fluid to make the streamline curve. So that's the force that causes the acceleration. If we look at the direction of the flow, again, we're going to ignore gravity, and then we're going to look at a steady state problem. And you can see what this equation now tells us is that the pressure change in the direction of the flow depends on the change in the velocity. So if dv ds is positive and the velocity is increasing, dp ds will be negative and the pressure will be decreasing. So as flow speeds up, its pressure decreases. While real flows, viscous flows, are much more complex than this, these trends are still valid. So even in viscous flows, pressure will rise as you move outward from the center of curvature. Even in viscous flows, pressure will decrease when velocity increases. And we can use these principles to make measurements and analyze real systems. Now, we can actually also find the pressure field in an incompressible flow. So if we have a velocity field, we'll assume we have steady state and we'll ignore gravity for this case. And so in that case, our equation is going to simplify where the pressure gradient only depends on the change in the momentum. So we can solve for the pressure gradient. We can expand it into our components. And so, for instance, in the x component, we can expand this vector equation out, and we get 3 equations, one for x, one for y, one for z. So if we know u, v, and w, because our velocity is given, we can find the pressure gradient. That's going to require us to have a boundary condition, right? We have to know the pressure at least one point. So we have the pressure at some initial point is equal to P0. So we can actually use Euler's equation if we know the velocity field to solve for the pressure gradients in the x, y, and z direction.